All right, so now we're going to go over calculating the freezing point depression and boiling point elevation for electrolytes. So the previous video went over non-electrolytes, which, as a reminder, are your covalent compounds. Electrolytes are going to be your ionic compounds, and they're going to be the aqueous in states of matter. Okay, so they're going to be your ionic aqueous solution or solutes. So when we put our, for example, salt or NaCl in water, it doesn't stay as NaCl. It's going to dissociate into sodium ions and chlorine ions, which means for every one sodium chloride we put in, we're going to end up getting two of these barriers or two ions out of it. So we get double the amount of blockage from the solvents bonding through intermolecular forces or attracting through intermolecular forces. So our ionic compounds are going to cause an even greater depression or elevation because of this fact that they're going to create more ions for every one molecule we put in. So we're going to go through and we'll do an example 17. I'll have you guys try one on your own. So this one's asking by how many degrees would the freezing point of water be depressed? So we know we're decreasing it, and we're talking about freezing point, which makes sense because we know that as we add a solute to water, it decreases the freezing point. It prevents that intermolecular force from taking place. But we're going to put 35 grams of lithium carbonate, and we're going to dissolve that in water. So we're going to be using our delta TF, because we're talking about freezing point, equals KF times M times I. So we're going to go through, we're going to look, and we're going to figure out our KF. That's always our first step because that's a constant. So we're going to go to our chart. We're going to find our KF, and we're talking about water. So we're going to look at the KF chart here. We said our solvent is our water, so we know it's negative 1.86. So KF is negative 1.86 molality over, degrees Celsius over molality. So then we need the M, and then we need the I. So the I is the quickest thing to find compared to molality. So we're going to go through and we're going to figure out the I. So we have to look at our solute because the solute is the thing that's going to ionize or break into ions if it's an electrolyte. So we need to look at lithium carbonate. So we know that this is an ionic compound because it has a metal, which is lithium. It has a nonmetal, which is carbonate. So we know it's an ionic, meaning when we put it in water, it's going to dissociate. So it's going to break into lithium ions, which has a +1 charge, and carbonate ions, which is -2. So now we need to balance it. So we need two lithiums. So we know for every one of these one molecule we put in, we're going to end up getting 3 ions. We're going to get 2 from lithium, and we're going to get 1 from carbonate, giving us a total of 3. So we're going to get 3 barriers for every one molecule we put in. Now we're going to find our molality, which just kind of reminder, molality is moles over kilogram of our solvent. So we're going to figure out our concentration, just kind of a reminder. The higher the concentration, the more change we're going to see in our freezing point or boiling point. Okay, because that means we're adding more solute, meaning we have more particles in the solvent blocking or preventing these intermolecular forces from forming. So we're going to go through, we're going to take the problem. So we have 250 grams of water, which we already know that's our solvent. So we're going to convert this into kilograms. So our molality equals 0.25 kilograms. All right, which means we have to find our moles. Well, we know we have 35 grams of lithium carbonate. So we're going to take our 35 grams of Li2CO3 and we're going to convert that to moles. So we're going to take our molar mass of lithium carbonate, which is 73.89 grams per 1 mole. Calculate that. We want 2 sig figs, so it'd be 0.47 moles of lithium carbonate. Put that on top. Then we just calculate our molality, which we're going to, again, we're going to round it to 2 sig figs. So this would be 1.9 m. So I'm going to plug this into 1.9 m. So compared to the video we saw yesterday or earlier, we should see a greater change here because we're adding an ionic compound. So we're getting more ions per molecule. So we're going to plug everything in now because we have all our variables. So delta TF equals KF times M times I. The I we do not count towards sig fig since it is a counting number. So we counted 2 plus 1 to get us 3. So again, we do not count that. So our delta TF, we just multiply everything out, is going to be negative 10.5 degrees Celsius. So by adding 35 grams of lithium carbonate, we're going to change water's freezing point by 10.5 degrees Celsius. So it is going to lower by 10.5 degrees Celsius. So again, when we add an ionic compound, we're going to see a greater change because we're going to have more ions produced for every one molecule. And again, the more ions we have, the more it's going to prevent these intermolecular forces. Okay, so this one, I want you guys to go through, and I want you guys to go through and calculate it, and try on your own, and I want you guys to calculate the change in freezing point. Okay, so it's asking for the new freezing point, so I'm going to have you guys calculate the change in freezing point first, and then we'll go through how to calculate the new freezing point. So when you calculated this out, you should have gotten a change of negative 5.58 degrees Celsius. Okay, so your I, just in case you didn't get that, so strontium hydroxide, you should have gotten the I as 3. Because we get 1 SR, 2 OHs, so we get a total of 3 I's. So if you didn't get that, so if you didn't get negative 5.58, that might be the reason. So this is our change in our freezing point. But the question's asking what would the new freezing point of a solution be of water. So in order to figure out the new freezing point, we need the change, but we also need another piece of information. We need to go and look at the normal freezing point. So normally, water is going to freeze at 0 degrees Celsius. So that is what water normally freezes at without any solutes added. But we added a solute and we changed it by negative 5.58. So in order to figure out the new, we're going to take our normal freezing point and we're going to add our change. Well, our change is negative, so we're going to add negative 5.8 degrees Celsius. So our new freezing point ends up being negative 5.58 degrees Celsius. So for water, the new and the change of freezing point is going to be the same since it's 0, but any other solvent will actually give you a different number. So if you notice all the other solvents, their normal is not going to be 0 degrees Celsius. So if you have to find the new freezing point, you have to look at, or even boiling point, you have to look at that normal first, and then you add the change. So we know that the new freezing point of water would be negative 5.58 degrees Celsius. So there's a problem at the end of the video, so I want you guys to try this, come with any questions that you guys have, and we will go over those in class.